Today I will be presenting an overview of a 2024 research article published in Frontiers in Energy Research by Chiu-Wing Chow and colleagues. This study investigates how a thermochemical composite system consisting of steam, foam, and viscosity reducers can enhance oil recovery in extra-heavy oil reservoirs, particularly those with erosion channels that develop during steam flooding. To explore this, the researchers conducted both rheological tests and oil displacement experiments using 1D and 2D sandbag models that mimic the complex reservoir conditions. These models allowed comparison between steam flooding alone and various enhanced techniques, including foam-assisted and viscosity reducer-assisted flooding. The key findings was that using at least 0.4% viscosity reducer significantly reduced oil viscosity and stabilized emulsions. When combined with foam, the composite flooding method led to a 30.46% increase in oil recovery in 1D models and a 16.61% increase in 2D models compared to steam flooding alone. While the results are promising, this study also notes several limitations. Laboratory models may not perfectly reflect field conditions, foam loses effectiveness at high temperatures, and the economic viability of these enhanced methods still requires assessment. In conclusion, this research shows that thermochemical composite flooding provides a synergistic effect between erosion and displacement, offering a potentially effective strategy for developing extra-heavy oil reservoirs.
The methodology used in this study is largely appropriate and supports the research objectives. The use of both 1D and 2D sandbag models, especially with erosion channels, adds realism and reflects actual reservoir complexity. The experiments were well structured, testing steam alone and in combination with additives like foam, polymers, and viscosity reducers. This allowed the authors to observe individual and combined effect on oil recovery. The measurement techniques, block dye tracing, oil recovery curves, and rheological analysis provided good insight into flow behavior. However, the method have some gaps. Foam instability at high temperature was acknowledged but not explored in depth. Also, there's limited validation of how closely the sandbag mimics real reservoir properties. Finally, the absence of uncertainty analysis or error margins weakens the reliability of the reported data. While the approach is practical, improving measurement transparency and model realism will strengthen the findings.
In the result of this study, thermochemical composite flooding demonstrated a significant improvement in oil recovery from extra-heavy oil reservoirs with erosion channels. In the 1D sandbag model, oil recovery increased by 4.38%, 17.38%, and 30.46% compared to steam flooding, foam-assisted steam flooding, and viscosity reducer-added steam flooding, respectively. In the 2D sandbag model, the addition of viscosity reducer and polymer to steam increased oil recovery by 16.61% and 19.24% compared to steam alone. The findings were well supported by recovery curves, water cut analysis, and visual dye tracking. Importantly, the interpretation identified erosion rather than displacement as the dominant recovery mechanism, emphasizing the synergistic role of foam and viscosity reducers. Overall, the data presentation was comprehensive and supports the conclusion that thermochemical composite flooding is more effective method for enhancing oil recovery under these conditions.
Moving on to the discussion of the study, this research primarily explores the operational mechanisms and effectiveness of thermochemical composite flooding in extra-heavy oil reservoirs that contain erosion channels. The discussion highlights how the combination of steam, foam, and viscosity reducers significantly enhances oil recovery. The authors used 1D and 2D sandbag models, and importantly, they incorporated erosion channels. These channels are often overlooked in traditional studies, but because they have high permeability, including them makes the study more realistic and closer to field conditions. One of the most important points in the discussion is the synergistic effects. Foam and viscosity reducers perform better together than individually, which leads to improved oil displacement and recovery. However, the discussion also acknowledged limitations. laboratory conditions are simplified, so field results may differ. In addition, foam stability at high temperatures and the economic feasibility of the method need further evaluation before field-scale application.
Now we will discuss on the reflection of the use of AI. Firstly, AI help us to improve understanding through structured summarization. The AI tools help us to understand the article more clearly by providing well-organized summaries. They wrote down the content into sections such as background, methodology, findings, and conclusion, which made the article easier to follow and analyze. Next, AI also provides us with a deeper identification of research gaps. The tools assist us in identifying meaningful research gaps that were not immediately obvious. For example, they point out issues like foam instability at high temperature, the lack of 3D modeling, and the absence of economic and environmental evaluations. These insights support a more thorough critical analysis. Third, recognition of novelty and impact. The AI tool help us recognize the originality of the study, such as the focus on erosion channels and the use of thermochemical composite system. They also explain the significance of the findings in practical and scientific contexts, which strengthen our understanding of the study's contribution to the field. Fourth, development of analytical thinking through prompt design. Crafting clear and focused prompts train us to think more critically about what information we want to extract. This process taught us that the quality of questions we ask strongly affect the relevance and depth of the answer we receive. Last but not least, AI as a support tool, not a final authority. Although the AI tools gave us valuable insight and save time, we still need to review and refine their response. This reminds us that AI support the process, but human judgment is still essential for academic and scientific accuracy. Here are the key takeaways message regarding the study. What the study is about. The study investigates how thermochemical composite flooding, a combination of steam, foam, and viscosity reducer, can improve oil recovery in heavy oil reservoir that suffers from erosion channels. What was discovered? The composite flooding method significantly increased oil recovery in both 1D and 2D sandpack experiments, showing a synergistic effect greater than the sum of individual methods. The main mechanism behind the improved recovery was enhanced erosion and expanded sweep. Why is it matter? Erosion channels reduce the effectiveness of traditional steam flooding. This study provides experimental evidence that thermochemical methods can overcome those limitations, making oil extraction more efficient in real-world conditions. What still needs to be done are further research is needed to address foam instability at high temperature, apply 3D reservoir modeling, and evaluate the economic and environmental feasibility of the method before large-scale field implementation.